Hello, my name is Benjamin Queck, and today I'll be presenting my deep learning project on using deep learning techniques to predict review scores. So my agenda today is I'll first discuss the problem statement, I'll talk about my data collection and preparation process, and then present my two deep learning approaches, being the dense sequential neural network and the LSTM network. So the supervised learning problem I've chosen is predicting the star rating given by a reviewer to a business based on the written review. This is a multi-class classification problem whereby we're trying to predict the review score out of 5. And this is a natural language processing problem. And the rationale behind this modeling approach is that the vocabulary used by a reviewer is going to be strongly linked to the rating they assign a business. So a poor review with lots of negative words will score lower, while a positive review with lots of positive words will likely score higher. So I obtained this data set from the Yelp Open Dataset, and this is a publicly available data set released by Yelp for educational purposes. The data can be found at this link and was extracted in July 2024. It contains almost 7 million rows of 150,000 businesses in 11 metro areas across North America. So this project will use the review JSON file, which contains 9 columns and about 7 million rows. The variables in this data set are listed on the screen. And for this project, the only variables of interest are the review score out of 5, so the stars column, and the written text component of the review. Only the first million reviews will be used due to computational constraints, and data checks revealed that there were no missing values or duplicates in the text. To prepare the data for modeling, two approaches were taken. Firstly, text vectorization with TF-IDF, or term frequency inverse document frequency, was performed using 1,000 tokens, and this looks for unique words and downscales the importance of common words. The vectorized data will then be used for a dense sequential neural network. And then text vectorization was performed to keep the text as a sequence of tokens for an LSTM model, and the stop words were also removed, removing common words which are unlikely to contribute to predictive performance. So the first deep learning architecture I chose was a dense sequential neural network. The input layer was the frequency of the top 1,000 words in each review, and 3 hidden layers were used in a final structure, decreasing from 128 to 64 to 32 neurons. And dropout of 20% was applied after each hidden layer to prevent overfitting. So the hidden layers use the ReLU activation function, and the output layer uses softmax activation function, as this is a multi-class classification problem. And the sparse categorical cross entropy loss function was used, again, because this is a multi-class classification problem. And we had 200 epochs with patience is 15 to balance computational efficiency with obtaining accurate predictions. So the model had an overall accuracy of 64% and a top 2 accuracy of 89%. So that means 89% of the time, one of its top 2 predictions was correct. By class, the model performs best on 1-star and 5-star ratings, as these have the highest precision, recall, and F1 scores. And the model doesn't perform so well in the 2 to 4-star range, which corresponds to what we saw in the EDA, whereby the top words for these star ratings were very, very similar, and was only the 1- and 5-star ratings, which had very different top words. So the second deep learning approach is the LSTM, or long short-term model, memory model. So this model is useful for processing sequential data, since it can learn long-term dependencies between data and prevent information loss. So the LSTM model had an input layer of 1,000 tokens, followed by the bidirectional LSTM layer with, followed by the embedding, and then the bidirectional LSTM layer with 24 neurons, and a 64 neuron dense layer, and the output layer. So again, similar to the previous model, we used a ReLU activation function in the hidden layer, a softmax activation function in the output layer, and we kept the loss functions, epochs, and patience the same as the dense layer, as the dense sequential neural network. So somewhat surprisingly, the LSTM model didn't perform better than the dense sequential network. The accuracy and top 2 accuracy are 1 and 2 percentage points lower respectively. So 63% for accuracy and 87% for top 2 accuracy. And overall, the F1 scores are the highest for the 1-star rating and the 5-star rating, and the worst for the 2 to 4-star ratings. Comparing the confusion matrices between the dense sequential and LSTM models, a similar pattern emerges. As already discussed, both models perform well at predicting the 1-star and the 5-star reviews. The LSTM model is slightly better at predicting 1-star and 4-star reviews, while the dense sequential model performs better with the 2, 3, and 5-star reviews. So this matrix also shows that the majority of incorrect predictions are only 1 point away from the true value. So for example, both models predict a significant number of 4-star reviews as 5-star reviews, but this shows that even though the model makes some inaccurate predictions, they're not far from the true values. So in summary, both deep learning structures perform similarly, with the dense sequential network slightly outperforming on accuracy. Similar performance metrics between the two models suggest that the models may be limited by the predictive variables available, and so high parameter tuning could help identify and reduce any overfitting or create a more appropriate model structure to classify the reviews. And alternatively, my EDA identified review length as a potentially significant factor, and this could therefore be incorporated into the model. Thank you.